Okay, so in this next section, this will be the first section for our second exam that we're going to have. In this first section, we're going to talk about derivatives of polynomials and exponential functions. So this is kind of like our nice, I don't want to say easy, but we're going to finally be able to do this in the faster way. We're going to be able to take derivatives and do it much quicker than we were before in the previous exam. So we want to build a few formulas first, and I won't make you build every single formula from scratch, but some of them we will, just so you kind of can get the experience on how a lot of the math that we take for granted was given to you, or now you can find it on your own. That's kind of the goal whenever I do a lot of proofs. It's not so much that I'm going to make you be tested on proofs, but I kind of want you to be exposed to this is how higher levels of mathematics is done. Any of you go on to be math majors, you're going to notice there's not a lot of numbers in your books anymore. But anyway, so I want to find f prime of x if f of x is x to the n. So this is just a general power function, x to the n. So what we're going to do is we're going to take the derivative of this, but we don't technically have the formula. So I do know the limit definition of derivative says the limit as h approaches 0. And then I'm going to do, remember, f of x plus h minus f of x all over h. So this would be the limit as h approaches 0 of x plus h to the n minus x to the n all over. So this is n, and this is h, okay? So now we're going to use the binomial expansion theorem. Let's see here. So we're going to take and we're going to expand this, okay? And this will become x to the n plus n times x to the n minus 1 times h. So basically what we're going to do is we're going to reduce the powers and then take the combinations for our coefficients. So then we're going to have plus n times n minus 1 all over 2 x to the n minus 2 h squared plus so on and so on. And again, this is not a test question. I'm just trying to show you how they develop some of these ideas. Nx h to the n minus 1 plus h to the n close minus x to the n all over h, okay? So, and again, all this is doing is basically expanding this. Like, so imagine that it was, you know, if you want, imagine it was x plus h squared. Well, that would be x squared plus 2xh plus h squared, right? So all it's saying is you take the power of n, so you'd have your x squared to the, you'd have your x term to the squared power. Then you reduce the power of x by 1, okay? And then whatever this power is, that's what goes right here. And then you reduce the power by 1 right here, and then you multiply by h. Then you take this value, n times n minus 1 over 2, and then you reduce the power of x by 2, then the power of x by 3, then the power of x by 4, so on and so on. So that's all the binomial expansion theorem is asking you to do. Don't stress too much about that. Let's see here. Oops. That was should have been from your pre-calc class if your teacher had time to make it to that subject. If not, if you're really concerned about it, you can look it up or we can go over it in class if you'd like. So all of this right here is just the expansion of x plus h to the n power, okay? So now we have this little minus x to the n, that's this guy right here. So now we got to do some cleanup. So what I'm going to do is I'm going to notice that every single one of these terms, notice this is positive x to the n, and this is minus x to the n. So those can cancel and become 0. And then I notice that every term has an h in it. And then, you know, these middle terms would have h's in them now as well. They'd just be reduced powers of h's. So what I'm going to do is I'm going to factor out in h. And let's see what that leaves behind. That's going to leave behind n x to the n minus 1 plus n times n minus 1 over 2 x to the n minus 2 times h plus n times x to the, plus h times n minus 2, because we factored an h out, so it's even one smaller than before, and this would be plus h to the n minus 1. Okay, and all of this, all of this would be divided by h. Okay, so now what we can do, is, let me see here, we have this h and this h cancel, and they become 1s, right? And that leaves us with n x to the n minus 1 plus n times n minus 1 over 2 x to the n minus 2 times h plus n x to the h, or xh n minus 2 plus h n minus 1. Now what we notice is this term, all these middle terms, and this term, all of the terms that would be generated from this all have an h in them, except this term. And if h is approaching 0, then this is going to become 0, this is going to become 0, this is going to become 0. And this is the only term that will not become 0. So then our answer, which is f prime of x, is equal to n times x to the n minus 1. And as it turns out, that is our formula for the derivative of x to the n. So let me write it formally. If, if n is an element of the reals and f of x equals x to the n, then, and again, this is for the basic general power function, right? Then f prime of x equals n times x to the n minus 1 for any constant c, the derivative d dx of c equals 0. And again, think of it this way. If you have 5, isn't 5 really 5 times x to the 0? And then this would become, if you wanted to say that f of x is equal to 5, then f prime of x would be, we take the power, right, of n, we put it to the front, and then we reduce the power by 1. But if the power is 0, this becomes 5 times 0 equals x to the negative 1. But it doesn't matter, that just becomes 0. That's just one way to calculate it. But in reality, remember what the derivative stands for. The derivative stands for the slope of the tangent line. But if the line, or the rate of change, right, the instantaneous rate of change, but if the line is not changing and the function is not changing, and it's a constant of 5, then the slope would be 0. Okay, so that's 2 ways you can think about it. You can think about it by taking the derivative like I just did, or you can think about what derivative means. There's more than that also, but that's just kind of what I would, my main 2 ways I would try to explain it to myself or explain it to others. Okay, so we have our general formula. Okay, let me see here. So this is our general power rule for derivatives. And the reason this will now come in handy is because if I ask you to use the formula, so I could say determine the derivatives of the following. And then, you know, I can have for number, oops, let me erase this. I don't really like how I following. Okay, so let's say we have number 1. Let's say we have y equals x to the 99. Okay, so then y prime would equal what? Let's say for number 2, we have d dx of 1 over x cubed. Let's see what that would be. And you know what, I'll write it below it right here. And then for number 3, we could say g of t equals t to the 3/2. Okay, and let me give you guys a few more to practice. Number 4 would be ddr of the 5th root of r squared. Let's see what that equals. And then number 5, let's do y equals 1 over the square root of t. And then let's do ddx of pi for number 6. Oops. So let's see what these equal. So why don't you guys take a minute to pause the video and give a shot or give these problems a shot using the formula you learned above, and let's see what we can do. Okay, so you guys should be back. So I want to find the derivative of all of these. Remember, this notation is Leibniz notation right here. This is just telling you to find the derivative. Here I'm saying what would y prime be worth? Here I could say g prime of t equals what? Here again, I could say y prime, and then, okay, so sorry, I forgot to write that on this. So now when we find y prime, we would be finding, we take the power, we put it in front, we rewrite x and reduce the power by 1. And that's it, that's all you do. Now imagine if you had to do that the limit definition way. That would be horrible, okay? So this power rule is gonna definitely help us for ease. Now what you really wanna get better at as well is taking radicals and exponents, or radicals and also negative exponents, and rewriting them. So this is actually saying ddx of x to the -3, right? That's another way to say it, because I didn't tell you how to do the quotient of 1 over x cubed, but you do know how to do the power rule. So what we're going to do is take the power -3, multiply it to the front, and then rewrite this as x to the -4 now, okay? And that would be our answer. Or you could even write it as -3 over x to the 4th, okay? But again, negative exponents are allowed in this class. The main reason you want to clean up fractions is when you're trying to find horizontal tangent lines when the derivative is 0. So a lot of times if you have fractions, you do have to clean it up, even if you have negative exponents. But for now, we're okay leaving that. So now we're going to take our power of 3/2. And remember, all I'm doing is it's saying whatever the power was, I write it in front and then multiply it times x and then reduce the power by 1. Okay, so that's all I'm doing in here. Take the power, write it in the front of the problem as a constant, and then rewrite t, reduce the power by 1. So 3/2 minus 1 would be 1/2, and we're done. That's our problem. So we have that, we have that. Now let's look at this one. So first things first, I'm going to DDR this, but I'm going to rewrite this as r to the 2 over 5 because I know how to work with exponents, but I'm not as good with radicals just yet in my derivatives. Rewriting them as exponents is much better. So now this is going to be 2/5 r. Now I subtract 1, so wouldn't it be -3 over 5? So this would be the correct answer, but depending on how it's asked, you could also be asked to write this. 2 over 5 5th roots of r, right? Cubed. That is the exact same answer. This is the exact same answer as this, except one of them is written with the radical in the denominator, and one of them is written as a negative irrational exponent, or not irrational, a negative rational exponent, okay? Now we have this. Once again, I'm going to rewrite this as t to the -1/2. So I rewrote the square root and the t in the denominator as a -1/2 power. Take the power, put it in front, rewrite the t, reduce the power by 1. So this would be -3 over 2. And this would be, once again, a correct answer. If you wanted to get fancy and they asked you to simplify in the homework, you would say -1 over 2, and then you would say the square root of t cubed. Okay, and then you'd probably have to clean this up. So that would actually be t square root of t. But again, I like this answer better. This answer is better to me. The only reason I would give this one is if they specifically asked for it, or I needed to solve, make common denominators or something like that. Okay, now what's the derivative of pi? Well, pi is a constant, right? It's approximately 3.14 today, tomorrow, the next day, last week. It's always the same. When you talk about pi, we're always talking about the same thing. So it's a constant. So the derivative is 0. We don't even have to do any work. Okay. So hopefully you guys are okay with that. Now we have a few more properties I want to write for you. Okay. So let's say differentiation rules. Okay. So if you take the derivative of a constant times a function, it is equivalent to taking, and you can take the constant out, you can take the derivative of the function, right? And then multiply c times f prime of x. Basically, this is the constant multiple rule. You're allowed to move when you're multiplying by like a 3, a 4, a -7, a 2/5, a 1.7 times some function. You can take that constant, move it out, and then put it back later once you found the derivative of the function itself. Okay. The other thing you can do is you can ddx f of x plus or minus g of x, and this would be equal to ddx of f of x plus or minus ddx of g of x, which is equal to f prime of x plus or minus g prime of x. So what this is basically saying is you can take the derivative term by term through addition or subtraction. Multiplication is a different story. The only one I told you right now is the constant multiple for multiplication. But if it was a function times a function, that's what we're going to need in the next section. But for now, whenever you have addition or subtraction, you are allowed to take the derivative term by term. Okay. In general, we don't write it out like this right here. We normally just say, well, we're going to take the derivative of this and we're going to end up with this. Okay. So normally we jump from here to here, but I wanted you to see that this is the in between. Okay. So let's take a look at a problem like that. So let's say we have find the derivative. Okay. So let's say that we have y equals 3x cubed plus 1 over x squared. And I want you to find the derivative. So you would just say y prime. And now I can take the, you know what? Let me write it like this. Let's say, oops, no. And actually in my notes, I have it as, or in Dr. Hughes's notes, I have it as f prime or f of x. So then f prime of x is equal. Now I have to ddx 3x cubed plus ddx 1 over x squared, right? But in reality, I don't want to have to write this out every time. So normally what I would just do is I would just say f prime of x is equal. Now take the derivative of this. So we have 3, that's the constant, and then we're going to move the power to the front, 3, right? This power is that. Now we have to rewrite x and reduce the power by 1, so it'd be squared. Now don't forget, this is actually, this is actually x to the -2. So when I do a derivative on x to the -2, that's going to be take the power, put it in front, so -2, rewrite x, reduce the power by 1, -3. So we end up with 9x squared minus 2x to the -3. So this is the correct answer, and we don't have to simplify it. We don't have to clean it up unless they specifically ask us to. Okay, let's find another one. Let's say that f of x equals x plus 7 times 3x minus 2. Okay, so if I take the derivative of this, the common mistake would be to take the derivative of this and take the derivative of this. You are not allowed to do that because this is multiplication. And the rules that I showed you up here are for splitting the derivative through addition or subtraction, or splitting the function through addition or subtraction and then differentiating piece by piece or term by term. So when I want to take the derivative of this, I can't. But I do know how to FOIL, so I could FOIL this out and turn it into an addition or subtraction problem. So this would be 3x squared plus 21x minus 2x minus 14. So again, I haven't done any calculus yet. I'm just rewriting this problem, and you will find that algebra is your friend in calculus. Okay, we're going to do a lot more than just algebra, but if you're good at your algebra, it will help you greatly in calculus. Now we can finally find f prime of x. I'm going to take the derivative term by term, piece by piece. This would be 6x plus 19 minus 0. So I don't need to write the 0, so I end up with 6x plus 19. And this would be my derivative, okay? So even though this was a product, I had a way around it. So we're going to learn a product rule in the next section. But for now, if you run into a product or a quotient, you got to use some kind of algebra technique to simplify it, okay? All right, so those were those two. Now, oops, you know what if I asked for the second derivative of each, okay, function. So the first derivative is the instantaneous rate of change, and the second derivative is the rate of change of the instantaneous rate of change. So that's what we often refer to as acceleration. So if the first derivative is velocity, then the second derivative is acceleration, okay? But mathematically, in order to find it, all you do is whatever the first derivative was, you take the derivative of the first derivative, and that gives you the second. So I would just write f prime of x equals 9x squared minus 2x to the negative 3. So then f double prime of x equals 18x plus 6x minus 4. What would f triple prime be if they asked? Well, it would be 18 minus 24x to the negative 5. And what if they said, what's f to the fourth prime of x, which they could? We would say, well, this is 0 minus or plus, what would that be, 120? X to the negative 6, okay? Okay, so this is our second derivative. This is our first derivative. This is our second derivative. This is our third derivative. This is our fourth derivative. And these are things that'll come up every once in a while in the class. Normally for us, second derivative will be as far as we go, but in calculus 2, we talk about differential equations, and then we can have the order of the differential equation, and sometimes it has a fourth derivative in it, so it has an order of 4, or it's a fourth order differential equation. But again, you can just keep taking derivatives. Notice here the notation, it started off as f prime, f double prime, f triple prime, and then after that, they pretty much start writing a little number there, 4, 5, 6, 7. They don't go much past that, okay? So let's look at this other one. If f prime of x is equal to 6x plus 19, then f double prime of x is equal to 6, and f triple prime of x is equal to 0, and f quadruple prime, to the fourth prime of x is equal to 0. So once again, this would be our first derivative, second derivative, third derivative, fourth derivative, okay? And again, because it was a polynomial, polynomials are kind of nice because there's an end in sight. No matter how many derivatives you take for any polynomial, eventually it will end and become 0. I shouldn't say end, that's the wrong usage. Eventually the derivative will become 0, okay? So in this case, the first derivative gave us a linear function. The second derivative gave us a constant function. And then anything after that, we know is just going to be 0 from that moment on because the derivative of a constant is 0, okay? So that's just something to think about for first and second, third, fourth derivatives. But again, for our class, we'll try to stick to first and second derivatives for the most part, okay? Okay, let's see here. I'd like to look at another one. Let's show, so if f of x is equal to e to the x, what does f prime of x equal? Okay. So we have to figure that out. Well, I don't know the formula for e to the x. So what do I do if I don't know how to find the derivative of e to the x? I'm going to say f prime of x is equal to the limit as h approaches 0 of e to the x plus h minus e to the x all over h. Okay. Well, that doesn't look super helpful because if I plug 0 in right now, I get e to the x minus e to the x, which is 0, divided by 0, and I don't know what that is. That's indeterminate form. Sorry about that. That's indeterminate form. So I'm going to do something that you normally don't do. Normally, if you had e to the x times e to the h, couldn't you rewrite that as e to the x plus h? So normally we multiply two same bases and add the exponents. But what if I wanted to take apart the exponents? Couldn't I go this way and say, well, what if I had e to the x plus h? So I'm going to write this as the limit as h approaches 0 of e to the x times e to the h minus e to the x all over h. And notice I'm multiplying. So if I multiplied those two, I would get this back, right? So it definitely works. I'm allowed to do this. So now I can factor out the e to the x. So let's say the limit as h approaches 0 of e to the x times e to the h minus 1 all over h. Okay. Now we know that e to the x doesn't need or doesn't depend on this limit of h. So as far as the limit's concerned, it can come outside of the limit. So I'm going to rewrite this as e to the, notice this is an h and this is an x. So they don't depend on, the e to the x doesn't depend on the limit. So I can kind of, it's not a constant, but as far as the limit's concerned, we can kind of treat it like that. So we're going to say the limit as h approaches 0 of e to the h minus 1 all over h. Okay, now we could create a sign chart, or you could take my word for it. You are not a sign chart. You could create a chart here, okay, and you could have h. Yeah, you could have h, and you could have e to the h minus 1 all over h, and you could try to plug in values, and you would find out that this limit based on this table is approaching 1. So this limit right here is actually approaching 1. So that means that we end up with e to the x times 1, which is e to the x. So what does that mean? What did we just find? We found that the derivative of e to the x is e to the x. So the rate of change of e to the x, the instantaneous rate of change of e to the x, is the function e to the x. So that means that f prime of x is equal to e to the x. So that leads us to a new formula for e to the x. So we say if f of x equals e to the x, then f prime of x equals e to the x as well, okay? So that's the best, right? That's the greatest derivative ever. So e to the x, and this only goes for e to the x. This doesn't go for like 2 to the x. 2 to the x, 5 to the x, those have a little extra added flavor to them, I guess you could say. So let's practice these. Find the derivative. Okay, so f of x equals x squared plus 3x minus 7 all over x. And let's say g of x equals e to the t plus t to the e plus 1 over, oh, I'm sorry, let me call this g of t, and then 1 over the cube root of t. Okay, so let's see here. Let's take this first one. Now notice this is a quotient, right? This is x squared plus 3x minus 7 all over x. But I don't know how to do the derivative of a quotient just yet of two functions. So what I need to do is I need to split it. I need to take this divided by this divided by this, and this divided by this. So that means that, and again, I'm not taking the derivative, I'm just rewriting. That would be x squared over x plus 3x over x minus 7 over x. So that means that f of x equals, and you could skip a little bit of this if you could do this in your head. This would be x plus 3 minus 7x to the negative 1. Now the derivative, I'm going to take term by term, piece by piece. This becomes 1 plus 0. Take the power, put it in front. This would be plus 7. Rewrite the x, reduce the power by 1. So that would be 1 plus 7x to the negative 2. Okay, and that would be our derivative. Now we come over here. Let me rewrite this real quick. G of t is equal to e to the t plus t to the e plus t to the negative 1/3. And once again, I really strongly encourage you guys to get better at exponents. If you're not great at them, you got to just keep working at it, because anything with powers, we know how to work with the derivatives in general, okay? But radicals and stuff in the denominators, you know, functions, it's a little bit harder. So we really love to work with powers, okay? So powers are very nice. So this becomes g prime of t is equal. Now, what's the derivative of e to the t? E to the t. Now, this is different. This is t to the e. This is not a exponential function. This is a power function. It just so happens that the power happens to be e. So I'm going to take the power of e, move it to the front, because remember, e is a constant. It's 2.71 and some change. So this will be t e minus 1 minus 1/3 t to the negative 4/3. Okay. And that would be my derivative. Now we're starting to see how it can get a little bit out of hand. That's a little bit uglier problem than we're used to working with. Okay. So, I guess we could do a normal line real quick. Oops. Okay, so let's do a definition. Let me do the definitions in blue. A line is said to be normal, okay, to a curve at a point if it is perpendicular to the tangent line at that point. Okay, so two lines are perpendicular, if you guys remember, if their slopes are reciprocal opposites. Okay, so if one of the slopes is 1/3, the other slope has to be -3/1. If one of the slopes is 5/4, the other slope has to be -4/5. So you should be able to always take two slopes that are perpendicular and multiply them, and you would get -1. So a line is normal to a curve at a point if it is perpendicular to the tangent line at that point. Okay, so let's see here. Let me write this one out. Okay, so there's that. So let's try this one. So let's say that we have find the equation of the tangent line, tangent and normal lines to the curve y equals x cubed plus 2x minus 3 at x equals -1. Okay, so let's see here. Let me see. Find the equation of the tangent line, tangent and normal lines to the curve y equals x cubed plus 2x minus 3 at x equals 1. So in order to find a normal line, right, it has to be perpendicular to the tangent line at that point. Okay, so that means we first need to find the tangent line. So in order to find the tangent line, we need a derivative. So that means we need y prime is equal to 3x squared plus 2. Okay, so I just took the derivative real quick. Now, you know, in order to find the equation of a line, we're going to need this formula. Y minus y1 equals m times x minus x1. But in order to use that, we need a point and a slope. So far, I have this point. So now I'm going to find y prime of -1, and this would be 3 times -1 plus 2. So this, squared. So this would be 5, I believe. Let me see here. Yeah. Okay. However, this is our tangent line because this is our derivative. We also need the point. Well, if the point is x equals -1, all I got to do is plug -1 into this, and it'll give me the y coordinate. So that would be what? -1 minus 2 would be -3 minus another 1. So we got -6. So this is our point right here, right? Oops. This is our point, right? -1, 6 is our point. So again, you guys kind of have to get comfortable. If they give you the x, then you technically know the y. You just sometimes have to work for it a little bit, okay? So now we're going to do y minus a -6 equals m, which is 5, times x minus a -1, okay? So we end up with y equals, oops. So y equals 5x minus 1, okay? Now, if we wanted to find the normal line, right? So the normal line, it says a line is normal to a curve at a point if it is perpendicular to the tangent line. So this is our tangent line. Okay, so this is our tangent line. So a normal line, I can already tell you, is going to be the same, or we're going to build it the same way. So this is our normal line. Okay, so we're going to do y minus a -6 equals, now instead of being 5, it's going to be -1/5, because that's what it would be to, what's the slope need to be perpendicular, is it has to be the reciprocal opposite of 5. So 5 is really 5 over 1, so this is -1/5 times x minus a -1. So now we have y plus 6 equals -1/5 x minus 1/5. Then we can -6 minus 6. So then we have y equals -1/5 x. What would that be? 6 1/5? Or you could say 31/5, either way. Okay. So, and technically, you could have left it here if you really wanted, and just made this a plus sign, made this a plus sign, and you could have left this here if you wanted and made this a plus sign and this a plus sign. Okay, you guys, that's going to do it for this first section. The next section we're going to go over is the product and the quotient rules, and I will talk to you about that in another video. Thanks for watching.